So I moved I moved the Monday one to a little bit later because apparently like the SL economics teacher, she wants to, I guess, do some online with you between 10 and 11, I believe. So I did move it to the Mondays one to later, 11:10. Um, Now you know by now that what they want to do is they want to do like a period per day, right? Period one, day one, period Monday, period two, Tuesday, and so on. Listen, I cannot sort of give you like one lesson. That would be like you would not sort of cover a lot of ground. So I still want to have like, well, initially it was 5 lectures, but I'm going to sort of move it to 4 lectures a week now. So for now, we're going to sort of keep it at 10:30 here from Monday to Thursday, and then Friday would be like a helping session of some sort. But what I'm planning to do, perhaps in the future, and I want to sort of get some feedback from you, is to give like perhaps like 2 lectures on Tuesday, and sorry, on Wednesday, and 2 more on Thursday. So basically what I want to do is I want to give a lesson like, let's say on Wednesday or Thursday at the same time, 10:30 or so, and then to have the second lecture on the same day later during the day, so around 2:30 to 3:30, and then reserve like Friday for helping sessions. So tell me like how you feel about this, if it works good for you. So it would be like only like only Wednesday and Thursday, so 2 sessions, like one in the morning at 10:30 and the other one at 2:30 in the afternoon. So I can sort of go through a lesson in the morning, give you some work to do, and then when you come back in the afternoon, well, you can ask questions and we can proceed. So let me know how. Yes, Phoebe,
Benjamin said that his computer died.
was that?
Benjamin said that his computer died.
Oh, that's too bad. Okay. Hopefully you'll get a. Whoa. Is it possible to move 2 lessons together? No, I think it's too. It's. No, I don't want to have a 2 hours lesson. I know you're almost adult now. Like some universities they have like 3 hours, but I don't want to do this. I want to give a 1 hour to have a break, and then you come back. 1 lesson per day might be better for getting homework done. Well, once again, like if I come in the morning at 10:30, right? I go until 11:30. That gives you a bit of time to sort of do some work before I come back at 2:30. And in any case, so you have like the whole evening, right, to work on that. Anyway, so for now, like, let me know about this here. So give me some feedback on the K-12. We may sort of talk about this also in a little while, but that might be something we can do. But for now, for this week, we're going to stick at 10:30, like every day until Thursday. Friday is Good Friday, so I'm not going to teach. No helping session as well. Monday is Easter Monday, so nothing as well. So there won't be anything on the program until Monday and Friday. I will not give any lessons, but next Tuesday I'll be back, right, at 10:30. All right. So any general questions? All right. No? Okay. So I will sort of start teaching. So once again here, we're going to sort of finish the force. There was only one topic that we didn't cover, so we're going to cover it. I'm going to give you an example, and then I'll give you some work to do. It's already on the website anyway, on the topic, and then we'll meet again like tomorrow at 10:30. All right, so let's talk about this. All right. So what we're going to do here is we're going to learn about something that's called Hooke's law. So it deals with springs. Now, please, like, be very, very gentle with me. I don't have any equipment at home, so I don't know if you can see this this little spring here. All right. So the property of a spring is that if I disturb the spring, it has a tendency to come back to its original form. There's what we call a restoring force to it. All right. It tries to come back to its original form. Also, if I compress it, the same thing, I can compress it. This one is pretty hard to compress. But if I compress it and let go, it tends to come back to its original form. Now, there's a limit to this. You can see here, like this one here, as being extended beyond what it can bear. So if you extend it like too much, it won't come back to its original form, right? But if I pull or push on it with reasonable force, it should sort of come back to its original form. And when it does, we say that it obeys what we call Hooke's law. So Hooke's law, Hooke was a British physicist, and he discovered a relationship between the force applied onto a spring as well as its extension or compression. All right. So okay, hold on a second here. Let me admit, like Benjamin. Whoops, it was someone else here, but okay. Uh, so bear with me. So let's say here that I exert a pulling force of, let's say, 10 Newton, okay? And then I measure by how much it has extended, all right? So let's see here, when I exert a force of 10 Newton, the spring has extended by, let's say, 1 centimeter, okay? All right, now, if I exert another force, let's say 20 Newton, I measure the extension of the spring, I can see that the extension is now 2 centimeter. Then I repeat, I exert like 30 Newton, I measure how much it has extended, and I see that it has extended by 3 centimeter. So you see here that there seems to be a relationship between the pulling force, the applied force, and the amount of extension. Can anyone sort of tell me what the relationship might be? I know it's based on three points, but what might this be? I'm waiting. You can talk. Yes, Madav.
It's a linear proportional relationship.
Very good. This is a linear proportional relationship. That's very good. So this is what Hooke's law is. Hooke's law relates the pulling force or the compressing force to the amount of compression or extension. All right. So I will go and make some notes. So let's do this here. So bear with me. Bear with me. All right, so everyone should see this. Can you sort of all raise your hand if you see this? All right, can you see all this? Raise your hand. Very good, very good, very good, very good. Excellent. Okay, so everyone seems to be all right. Okay, so lower all your hand. Okay, so let me sort of do something before I start. There we go. All right, so let's start. So Hooke's law. This is a very bad term, Hooke's law. It should be like Hooke's rules, because the law is not supposed to be violated. We're not in chemistry. We're in physics. So physical laws are not violated, right? They don't get broken. So it should really be called Hooke's rules, because it does break down at some point. Okay. All right. So Hooke's law, it looks like this. So let's say we have a spring. All right, so here's your spring. Okay, and this is the original length of the spring without extension or compression. Is called the equilibrium length, or sometimes it's called the rest length. Okay, so I'm going to call this the equilibrium length, so EQE. I'm going to put this on the board, don't worry. Okay. Now let's stretch it. 1, 2, 3, 4. So 1, 2, 3, 4. So there you go. So I'm pulling it. And I'm pulling it with a certain force. So let's see here. This is the applied force. And of course, like the spring has a tendency to resist me, right? So there's a restoring force called, in this case, the spring force. So of course, the spring exerts a force on me. All right, so we'll go and call this like the spring force. Right? And this is a restoring force. Now, when I stop like pulling the spring, everything is at rest. So the applied force will be equal to the spring force. Okay. Now, this is the amount. So this is by how much has been extended. Right. So we're going to call this X. If you want to ask me a question, please like go on the speakers, because I don't have a tendency to look at at the camera. So if you want to catch my attention, if you raise your hand, I will probably not see it. So make sure that you.
Sir,
yes.
What does that say?
Where?
Like the.
Where? The spring here?
Like below the spring in brackets.
Oh, restoring force. Okay, so let me do this.
Okay, thank you.
All right, let me do this. Nice. Okay, so whoops, I want it in red. All right, so whoop. I have to go back. Sorry, guys. I hope it's still there. There we go. All right, so I don't know why I cannot get. That's why. Okay, not totally familiar with this. So restoring force. Okay, not any better than before. So, all right. Yeah, it looks like a J, right? Restoring force. Okay, so delta X. Delta X gives you, so delta X is X minus the equilibrium length. All right, so this is the amount of compression or extension of the spring. All right, so let me sort of put this here. So XQ here is called the equilibrium length. Length of the spring. Also called the rest length. All right, so there's no force applied on the spring. That would be like the extension or the length of the spring. Okay. So you notice here that if delta X is greater than 0, what are we dealing with? Anyone? Delta X is greater than 0. So yes, Max. Yeah, Max.
Extension.
Very good. So this is extension. And of course, when delta X is smaller than 0, this is compression. All right. Now, I repeat, I will not sort of use the sign, okay? From the problem, you're gonna find out in which direction the force of the spring is, and that's it. So we're gonna always sort of use the absolute value of delta X. So I will not sort of use the sign for delta X is positive for extension, delta X is negative for compression. So that would be the absolute value. And I will just make sure that I get my spring force in the proper direction. Okay. Okay. So let me see here. Like some other people wants to Rayleigh. Okay. It was not in. Okay. All right. Good. All right. So the spring force. So the spring force is a restoring force. Okay. And from now on, I'm going to put Fs for the spring force. I will not use E. Some people use E because it's elastic force, but I reserve E for electricity. So that's why I don't put like Fe. I'll put like Fs for the spring. Now that works well for English, but doesn't work well for other languages. But I'll leave it like this. Okay. So it's a restoring force. So once again, if you extend it, the spring force will be to restore it in the opposite direction, while the applied force. If you compress it, the spring force will be in the opposite sense, in the opposite direction. It will still be opposite to my applied force. Okay. Okay, so as I said earlier here, what we know is that the spring force is proportional to the amount of extension or the amount of compression. So if you extend a spring like twice as much, the force in order to extend it twice as much will be twice as big, right? So you will need to apply a force twice as big. If you want to extend it by 3 times as much, you have to apply a force that will be 3 times as much. So the spring force, the restoring force, will be 3 times. Okay, so who wants to come in? Okay, Benjamin. Okay, so let's hope it works for him. All right, so this is Hooke's law. All right, so this is Hooke's law right here. Okay, so the spring force is proportional to the amount of extension, linearly proportional to the amount of extension or the amount of compression. As I said earlier, it should be called a rule because past a certain point, this is no longer the case. All right, so if I extend this like really, really much, right, at some point it doesn't obey Hooke's law anymore. Okay, but we will always assume that we extend or compress the spring in such a way that it obeys Hooke's law. So we say that it is in the linear range of the spring. Now, you remember here, whenever we have a directly proportional relationship, we can always turn this into an equation, provided that we put what? Anyone?
Of proportionality in front of it?
Yeah, that's correct. Constant proportionality, and this is exactly what we're going to do. All right, so we're going to put a constant proportionality here. And a constant proportionality in this case here is called K. All right, so this is Hooke's law again. So where K is called the spring constant. All right, and so this is a measure of how stiff the spring is. The spring is. All right, so it's a measure. This is my key, by the way. Okay, so get used to it. All right, you should. Okay, that's a K. It's not an R. It's a K. So it's a measure of the stiffness. All right, so a very high spring constant means that the spring is very stiff, and if it's a low spring constant, it's very easy to extend or compress. No, can anyone tell me what would the unit of a spring constant be? Anyone? Raise your hand and talk. Or else I'm going to choose one. Yes, Max again. Wow. Likes to talk. Yes, Max.
Is it newtons per meter?
Very good. So Newton
Oh,
per meters. That's
a-
excellent. That's excellent. All right. So it's in Newton. So unit is Newton per meter. All right. So let's do an example here. By how much would a spring with a spring constant of, let's say, 2000 Newton per meter. Okay, about how much would a spring extend if an applied force of, I'd say, 500 Newton is exerted on the spring. So about how much would a spring with a spring constant of 2000 Newton per meter extend if an applied force of 500 Newton is exerted on the spring? All right, so this is pretty easy here. So what do we know? We know the givens here. We know the spring force. Okay, so if I'm applying a force of 500 Newton, of course, it doesn't move, right? So the spring exerts a force of 500 on me. So that's a restoring force. That's a spring force. And of course, it's going to be the negative direction, but I don't want to put like negative direction here. All right, so we'll do, for now, we know that the spring force, the absolute value of the spring force is 500 Newtons. We know also the spring constant, so we're looking here, we're just looking for that. So this cannot be like any easier. You just isolate for delta x. So you bring your delta x on, you bring your k on the other side. And that will give you 500 Newton over 2000 Newton per meter. And of course here, the Newton will cancel. You're going to be left with 1 over meter. So a reciprocal, when you divide the fractions, the same by multiplying by its reciprocal. So it's going to become like meter per meter over 1. So it's going to be meter. And of course here, that's going to give you, so 5 over 20. So it's a quarter, right? Is that it? So it'll be like 25 centimeter. Am I good? Yeah, 5 divided by 20 is a quarter, right? Yeah, thank you, Max. Thank you. I appreciate it. Okay, are you good? Are you good with this, guys? All right, so why did I say that the spring constant gives you the stiffness, measure the stiffness of the spring? Because if you put like, you see here that the spring constant is 2000 Newton per meter. If I ask you how much force would I need in order to extend the spring by 1 meter? Well, you would put like 2000 Newton per meter times 1 meter, and it gives you 2000 Newton. So this is what you would need, the force you would need to apply to extend it by 2000 Newton. Now compare this to a spring whose spring constant is only perhaps like 50 Newton per meter. Well, 50 Newton per meter, what it means you need to exert a force of 50 Newton to extend it by 1 meter, right? So whereas this one here, you needed, the one before, you needed 2,000 Newton. So that's why the spring constant gives you the stiffness of the spring. So very high spring constant, it's very stiff. You require a lot of force to extend it or compress it. All right, is everyone okay? All right, so let's do something a little bit more, whoops, a little bit more difficult here. Well, it's not really that difficult. Okay, so let's do another problem here. A 20 kilogram block is pulled with a spring. It's pulled with a spring. And we're going to say like K here is equal to, let's say, 500 Newton per meter. So again, if you have questions, just yell. Well, not yell, just talk. All right, 20 kilogram block is pulled with a spring constant this, and across a horizontal rough plane. So 20 kilogram block is pulled with a spring across a horizontal rough plane. If it accelerates, sorry guys, let's accelerate with, let's say 3 meters per second square. And the plane exerts. You know what? I think we'll make it like more difficult here. So it'll be a good review. Okay, and the plane, so let's see here. The plane has a coefficient of kinetic friction of, let's say 0.2. Okay, so if it accelerates with 3 meters per second square and the plane has a coefficient of kinetic friction of 0.2, find the extension of the spring. Find the extension. I'll put this a little bit more. There you go, a bit more. Extension of the spring. Book. All right. So I'll just wait for you to finish copying. So a 20 kilogram block is pulled with a spring across a horizontal rough plane. If it accelerates with 3 meters per second square and the plane has a coefficient of kinetic friction of 0.2, find the extension of the spring. Okay, so the first thing here, so let's have like little system diagram here. So remember, system diagram is the outline of what's happening here. So this is your box, your block, and someone is pulling with a spring. And the force, we don't know the force, right? So no. Very good. So that's the system diagram. I did not put all the force here. Let's put the direction all the time. So forward will be x, positive. Up will be positive. And what we're looking, of course, for delta x. Now we know K. We know that K is 500 Newton per meter. Well, there's only one equation we can use for this. It's Hooke's law, right? That's the only one that we can use here, right? So we can use only this one. Now we have K. We're looking for delta x, of course, and we don't have the spring force. So one way or another, we have to find the spring force. So how are we going to do this? Well, we're going to go back to Newton's laws of motion, right? Second law of motion. So we're going to do an FBD. So let's do an FBD here. You remember, so, whoops. Whenever I put something in orange, it's always something like a review or something I don't want you to take note. All right, so you'll know now. There you go. All right, so let's do an FBD of the block. All right, so we have the spring force. What else do we have? Raise your hand.
The weights.
Yeah, raise your hand first. Yes, Max. Always, okay, yeah, Madav.
The weights.
The weights, okay, so which is gravity, right? And it's going to be down, right? Okay, so we're going to put W. Okay, what else? You can lower. Yeah, Nikki?
Friction.
Friction in the opposite direction. Very good. And this friction will be what type? Raise your hand. What type would this be? Ditya?
Kinetic friction.
Yeah, kinetic friction. Sorry, Luke. Next time. I'll ask you. Okay, Luke. So what's the last one? Yeah, you don't have to raise your hand. I called you out. So what's the last one? Can you talk? Are you chatting now or what? I cannot hear.
Normal force?
Normal force. Okay, you have to be closer to your mic or change the mic. Right, normal force. Very good. As always, you can sort of put like V here. So I know in which direction this thing is going. And once you have the FBD, like the rest is pretty easy. So let's do x-axis. So x-axis. So remember here, the net force along the x-axis is equal to mass times the acceleration in the x-axis, right? All right, good. So what do we have in the x direction? Well, we have the spring force, right, which is in the positive direction. So I'm going to do positive minus the friction. And this is going to be equal to this. We're going to drop like the x because that's the only acceleration we have. So we don't have to carry the x there. Now, you remember that this is equal to friction is equal to coefficient of friction times Fn. So you see here that in order to find the extension, let me sort of use a, there you go. Woo! So there's a pointer here. Ooh, you see the pointer? Ooh, that's cool. All right, so in order to sort of find this, we know that, so we need to find the spring force. Well, in order to find the spring force here, you need the acceleration and you need this. You already have the acceleration. So let me put it back here. So we know the acceleration, and the acceleration will be, of course, positive, and it's 3 meters per second square. We know the mass. So if we know the mass, we know this term. In order to isolate for the spring force, we need to find this term. Well, we can find this term, of course, by going in the y-axis. So let's call this like number 1 here. So let's look in the y-axis. What do we have in the y-axis? Well, the net force in the y direction is equal to the mass times the acceleration in the y direction. But what do we know in the y direction, guys? What do we know about the acceleration in the y direction? Yes, Madav.
You can figure out the weight using the mass and the
No, but
gravitation.
okay, but before that, what do we know about the acceleration of this block in the y direction?
It's 0.
Yeah, it's 0 because it's, Nikki, yeah, because it's not moving.
It's not moving up
Yeah,
or down.
very good, excellent. So this is 0 because no motion. Along y-axis. Very good. All right, so what do we have here? We have that, so what do we have in the y direction? We have Fn minus the weight equals 0. So therefore, Fn is equal to the weight, because there's nothing else along the y direction except the weight and normal force. So in this case, normal force is equal to weight. And we know that the weight is equal to mg. So it's going to be like 20 kilogram times 10 meter per second square, right? And it'll give us like 200 Newton, all right? So now we know this and we know that, so we'll be able to solve for the spring, right? So if I isolate like Fs here, I get this. If I put it on the other side, it becomes this. Now I can put like the values. So it's going to be like 20 kilogram times 3 meter per second square plus 0.2 times 200 Newton. So that gives 60 Newton. So this one will give me 40, I think. Okay, if I make a mistake, let me know. And so that gives like 100 Newton. Right? So now we know like the spring force, we know K, so we'll be able to isolate for the extension. All right. So we use Hooke's law, equal to this. And delta x is equal to fx over k. And that's going to give us 100 Newton. What was k again? 500? Yeah, so 500 Newton per meter. And that will give us 0.2 meter or 20 centimeter. And then you box the answer. Woo! Doop. All right. Okay. So that's a good problem here because it forced us to review most of what we learned in the force unit. So coefficient of friction, spring, using like the x, the y-axis, using Newton's second law, and so on. All right. So questions? Can you raise your hand? Yes, Max.
So for the part where you wrote Fn equals to weight equals mg equals to 20 kilograms times 10 meters per second squared. So 10 meters per second squared, it's not negative even though.
No. That's what I said. No, you never use, no, like the signs, the negative sign here will be always here, okay? So if a force like here, right? So force here is a negative direction, so you put a negative here. So the force here, this is always like positive. It's always the absolute value. Like this here, it's always absolute value. Never put, you never put like a negative sign there. Okay.
Oh, okay. All right. Thanks.
Yes, Madav.
When we're showing our work for how we found Fn, should we show
Yes.
the y-axis steps, or
Yes.
can we?
Yes.
Okay.
Yeah. Don't go and say Fn is equal to weight. All right. I need to know why. Okay. Yeah. You have to be very diligent about this. Yeah. Any other questions? All right. So if you go on the website, you're gonna have like some work for this. So just work on that, on the spring Hooke's law. I will sort of remain like online here for just a few more minutes. If some people have missed like taking my notes here, I'll go back up and then I'll go like slowly. So tomorrow we'll meet by 10:30. About 10 minutes before I send like the invitation. So get ready at 10:20. As I said earlier here, this week we'll have like 10:30 like every day until Thursday. Friday is Good Friday, so want to have a lesson, okay? And I want you to think about like the suggestion I made of having 2 lessons, one in the morning, one in the afternoon on Wednesday and Thursday, and just let me know in your comments here in K-12, let me know how you feel about this. Okay, I may sort of send a Google form and see if we can get like a survey of some sort. Yeah, more. Okay, so what's happening here? Chat. Yeah, what do you want? Chat. Hold on a second. Yeah, let me put this on this side. 1 lesson per day might be better. Oh, that was before. Sorry, my internet cut out. Okay, Ray, that's fine. So for the physics contest, you can launch a poll on Zoom. Oh, I don't know how to do that. Well, perhaps next time. I want people like to think about this, all right? And I'll find out about this poll on Zoom. Okay, for the physics contest, I don't know yet. I don't know if I have to sort of check for the grade 11 if it's still on. I'm not so sure. If it's too much of a trouble, I'll just
Leo's asking the big question
but
right
we'll
here.
see. Just let me know.
Let's see it.
Sir, how should we end the? I said the ICU. Just keep it for now, okay? But I hope it's done because I mean, without much.
Yes, sir. Yes, sir.
I may sort of
Yes,
ask you
sir.
like within like I don't know 3 hours or 4 hours to submit it, okay? So
What
I
the
want to make sure that
Wait,
everyone has
how
done
do you do
it,
that? How you gonna
okay?
submit it?
But for now, like don't
Since it's
don't
long,
head it in.
probably.
Any other questions?
Might. Anyway, I don't know.
Let me check if I did it all.
Okay. All right. So as I said, like you can, if you want to disconnect, you can disconnect. I will let it run for
Hard.
5.
Yo, Michelle Dick's the
Or-
best, bro.
Yeah,
Come
7
on.
minutes if some people wants to ask me
Wait, you
any
finished 20 minutes
questions. If some people wants to,
That's pretty good.
if they haven't sort of
Respect for that,
written
actually.
everything, I can sort of go
Wait, guys.
back.
Guys, what about the 1 p.m. to 2 p.m.
Okay.
thing?
Yeah, what was the very
All right.
first thing he wrote? Like besides
So
the
until
graph?
tomorrow,
Besides the what?
Until tomorrow? Hashtag until
take care of
tomorrow.
yourself and your family, and don't forget physical distancing, guys. All right.
Just dancing. Okay, I'm out
Okay.
of
So
here.
God bless.
Yeah, I'm
and
outta
I'll see
here.
you tomorrow.
Hog.
Peace out, boys.
As I said, I'll stay there here. Yeah, Max.
Pog.
Hey, yo.